Hi everyone, my name is Jose González Abad and I am a postdoctoral researcher at Instituto de Física de Cantabria in Spain. I work in deep learning for climate sciences, although my main line of research is deep learning for statistical downscaling. That's why today with this tutorial, my aim is to give you an introduction on how we are using deep learning models for statistical downscaling. However, I would also like to focus on give you an introduction to statistical downscaling itself. So my idea is that at the end of this tutorial, you are able to understand what is statistical downscaling, why it is useful, and how we are using deep learning models for, well, to improve the statistical downscaling that we are doing at this very moment. Here is the table of contents of the tutorial. This video is just an introduction to the tutorial. I will talk about some ideas, but these ideas are explained in more detail in the notebook itself. So I really recommend to look into the notebook and try to understand, to have the whole picture of statistical downscaling and deep learning statistical downscaling that you can get from the notebook. This is the table of contents. I will mention a lot of things about the data, about the statistical downscaling itself, the deep learning models that we use for statistical downscaling, and we will work with real data within the statistical downscaling, and we will train and make predictions with a deep learning model, and we will see what is the potential of statistical downscaling, but also deep learning models for statistical downscaling. So to simulate, for instance, the evolution of climate change into the future, we rely on climate models. There is one kind of climate models, which are global climate models that allow us to simulate the climate in the whole planet in, centuries ahead. The issue with these climate models, these global climate models, GCMs, is that they are computationally expensive. So they are not able to work at high spatial resolutions. As a result, as a consequence of this computational complexity, the simulations of these climate models are coarse. They have low spatial resolution. Of course, this is an issue because we cannot work at regional scales, at local scales with these simulations because we don't have enough detail due to this low resolution. But the other problem that we face is that given the fact that GCMs are not able to take into account regional spatial resolutions, they are not able to simulate local processes that may be relevant for the evolution of different variables into the future. So a solution to this is downscaling. The idea of downscaling is to take these coarse spatial resolution variables and try to get a high resolution version of those variables or of some specific variables, thus being able to generate simulations that we can use to local studies or to apply at regional scales. There are several branches of downscaling, and in this tutorial I will focus on statistical downscaling. The idea of statistical downscaling is to use a statistical model to learn the relationship between the coarse scale, the low spatial resolution variables that we get from the GCM, and the high spatial resolution, the local variables that we need for regional applications, for instance. So in this tutorial, I will try to give you an introduction to statistical downscaling, an introduction with the kind of data that we work with in statistical downscaling, and of course about deep learning models for statistical downscaling. Of course, the impact of statistical downscaling is quite relevant, right? Because if we want to perform studies at regional scales, we need to have regional data, regional simulations into the future, right? For instance, I don't know, imagine that I want to know how precipitation is going to change in the future in my city or in a specific region within a country. In that case, I need to have high resolution simulations, and one of the most popular and most important ways of doing that is through downscaling. Of course, we have several approaches to downscaling, as I will try to mention later, but statistical downscaling is quite promising because statistical models and deep learning models are not that computationally expensive. So we can generate a lot of high regional simulations into the future without having to rely on huge clusters or on thousands of CPU hours. Here I have mentioned some important concepts that I think is interesting for you to get familiar with if you are going to work in statistical downscaling. I would say that from a technical aspect, statistical downscaling is not that challenging field. However, we have to handle a lot of terminology and a lot of concepts, and that may be confusing for people that is not familiar with the statistical downscaling field. That's why here I have tried to put together a series of concepts that I think are useful to know or to be familiar with if you are going to work with statistical downscaling. I would like to emphasize some of them in this video, although you can always get more details from the notebook itself. For instance, we have already talked about global climate models, but we also have regional climate models. Regional climate models, or RCMs, are the tools that we use within a specific branch of downscaling, which is dynamical downscaling. This is a physics-based model, but instead of running on the whole planet as a GCM, it only runs in a specific region. So we can increase the resolution in that region and as a consequence get high resolution simulations in that region. The issue with dynamical downscaling is that it is computationally expensive, so it is not easy to generate simulations for different GCMs or different future scenarios because we require a lot of computational power. And actually that's why statistical downscaling is interesting, because we can do the same without having to run these expensive regional climate models. Another aspect I would like to mention is perfect prognosis statistical downscaling. Perfect prognosis statistical downscaling is a branch within the statistical downscaling which defines how we train the statistical model to go from the coarse resolution, from the low resolution of GCMs to the high resolution that we aim to get, the high resolution that we need. I will not go into the details right now, but later I will try to give you an introduction to perfect prognosis statistical downscaling through a scheme that I have included in the notebook. Again, you can find more details in the notebook itself. Regarding the software that we are going to need for this tutorial, is quite simple. We need NumPy, we need Pandas, we need Matplotlib, and we need XRI. XRI is a library that is used within Python to work with climate data because climate data has a specific format, netcdf. If you are not familiar with XRI, you don't have to worry because I have tried to abstract that part from the tutorial. Anyway, it's quite simple to use. It's quite similar to NumPy and this kind of related library, so it should be quite straightforward to work with it if you have already worked with NumPy or Pandas these kind of libraries. For the deep learning models, I will rely on PyTorch, which I think uh, is the standard regarding deep learning research. So I guess most of you are familiar with it. If not, again, you don't have to worry because the code is abstracted. So in case you don't want to get into the details of the implementation or the code, you can always get the message of what is statistical downscaling, how we train deep learning models on it, and so on and so forth. So here I have prepared a couple of chunks of code for installing the required libraries in the Google Colab. You can import that libraries in the Google Colab. And then you have this part of the notebook, which is the configuration. Here I have included some parameters that define some aspects of the tutorial or of different parts of the tutorial. The idea is that some of these parameters can be done. You can you can change the values, so to speak. So you can try to play with, with different aspects of the tutorial to change different things. For instance, here you can see some parameters that you can change for the deep learning model. Imagine that, as we will see later, that I want to try to train the deep learning model for longer. Well, in that case, I can increase here the number of epochs. I can run the tutorial again, and the model will train for that number of epochs. So this is some kind of configuration, so everything is clear, but also so you can play with different parameters and different, configurations of different aspects of the tutorial. Regarding the data, we are going to use a real data set that is being used in the statistical downscaling community, and that is the Cordex machine learning benchmark. Here you can find the GitHub of the benchmark. This is at this very moment the main page of the benchmark, in case you want to know more about it. But the idea of this benchmark is to provide a wide spectrum of datasets to train deep learning models on it for statistical downscaling, with the idea of try to intercompare different deep learning models, different deep learning architectures, training paradigms, and so on and so forth. So we can get an idea of what deep learning models work the best over a standard evaluation framework. So given the fact that this data is open source, is as a node, we are going to use this data for the tutorial as predictors, and I will give you a bit more of detail later, but I have decided that it's better if you look into the notebook to get a better idea of why we use certain predictors and what we use certain predictors. But as predictors, we are going to use a set of large scale atmospheric variables that represents the state of the atmosphere. This is what the deep learning model is going to use to compute the predictions, to compute the predictant. And of course, the predictant is the high resolution variable that we are interested in downscaling. For instance, if I want to study how precipitation is going to change in my specific city, then the predictant is going to be precipitation. That's the variable that I want to downscale. I will give you more details about the predictors that we use later. We are going to use different periods for training, for evaluation, and so on and so forth. The idea, of course, this evaluation is way more complete in the benchmark. This is like a small subset of the benchmark. But the idea is to be sure that the model that we have trained in a historical period is valid for downscaling in the future. That's why, as we will see later, and as you will see in more detail in the notebook, we train in this period, for instance, and then we compute predictions and we evaluate the model in 2 different periods in the future to see, for instance, how well the model is able to extrapolate when being trained in a historical or a present period. The data, as I said, the data for the benchmark is available in a Zenodo. However, the whole data set is quite large because it covers different domains, different variables, and so on and so forth. So I have created for this tutorial a subset of this benchmark dataset, so you can work with it either in Google Colab or your local PC, and you don't have to dedicate a lot of time to download the data. I think that this subset version is around 3 gigabytes, so actually it works fine on Google Colab. You should be able to work with it without any problem. So in this chunk of code, you have all the required code to get the data from Zenodo and to save the data in Google Colab. If the data is already present, it will skip the download of the data. Otherwise, it will download the data from Zenodo and it will save it as required for the rest of the tutorial. Again, this shouldn't take much time, so you can download it, wait a couple of minutes, and you should get the data ready to work with. So before training the deep learning models, I thought that it was interesting to try to show you what is statistical downscaling and what we aim with it by playing with a little, use case, right? The idea is that imagine that I live in New Zealand and I want to assess how climate change is going to impact in my specific city or in my specific region. Actually, this is New Zealand. Imagine that I want to assess how precipitation is going to change under climate change, is going to change in the future for these two specific locations, the West Coast and the Southern Alps. In this case, what I'm showing here is the daily precipitation for an historical period at a high spatial resolution. 10 kilometers can be considered a high spatial resolution. What we can see is that the mean precipitation across these 2 points, which if you notice they are quite close together, they are not far apart. Actually, I think they are 40 kilometers apart, something of that kind. We can see how the precipitation is quite different. In this point, in the West Coast point, we have 6 millimeter precipitation, whereas in the Southern Alps point, we have 22 millimeters precipitation. This is the mean precipitation for this period. Why we have such difference? Because this point, the Southern Alps point, is located in a mountain region. So there, due to some local processes, precipitation is higher than in the West Coast, which is a point close to the coast with with no height in a flat area. So here we can see the typical example that two nearby points may show different properties for certain variable, in this case precipitation. So what would happen if instead of having this high resolution daily precipitation, I have the precipitation simulated by a GCM? Remember that the issue with GCMs is that they have a low spatial resolution. They have a coarse spatial resolution. Actually, here you can see the resolution. You have one value for this area. This is the resolution that we have. Of course, this is an issue because in this case, we don't see the contrast between these 2 points. We can see how these 2 points have a similar value for mean precipitation. However, the reality is different. The reality is that if we take into account that regional detail, all those local processes, we find that the precipitation is quite different between the 2 points. So by taking into account the simulation of the GCM, we are losing a lot of detail because the GCM is not able to get is not able to simulate those regional processes. It's not able to simulate this kind of regional projections. Instead, what we get is this coarse precipitation simulation that doesn't allow us to assess the difference between the two points. So here we can start being aware of the issue that we have when working with simulations from GCM, if of course we want to work at regional scales. We don't have that regional detail when working with GCMs. And actually that also applies for the future, right? Imagine that this is the simulation of the GCM for a historical period, but imagine that I compute the climate change of the simulation of a GCM. The climate change is just the difference between certain variable in the future in comparison with some historical period. Here again we see the same effect. For these 2 points we don't see differences, or the differences are not that large. In this case, in the climate change, in the precipitation change, in the climate change signal of precipitation. So in other words, how precipitation is going to change into the future in comparison with the present or an historical period. In this case, we can see how the GCM projects almost no difference between the 2 points. However, if we take that same change, that same climate change projection, but instead of from a GCM, we take it from a regional climate model. Remember that regional climate models, RCMs, are the tools, are the models that we use in dynamical downscaling. And actually this is just a similar model to a GCM, but focus on this area with a higher resolution instead of the global extent that the GCM covers. Because here I'm just showing the GCM over New Zealand, but the GCM is able to generate simulations across the whole planet. So here we can see the difference. If we take into account the GCM to assess climate change in these 2 points, we will get something that is not close to a potential reality. Why? Because the GCM is not able to get this local detail. Actually, if we compare the values with an histogram, we can see how well. For the West Coast, we get a similar signal between the RCM and the GCM, the dynamical downscaling model. Remember that, the RCM and the GCM. But for the other point, the one located in the mountains for which regional processes are quite relevant, we see a huge difference between taking into account the regional processes, something that the RCM is able to do, versus not taking them into account, something that the GCM cannot do due to the limitations that we have mentioned so far. So this is the problem that we are trying to solve with downscaling. We aim to generate a high resolution projection from this GCM so we can get something like this. Of course, we could do this with the RCM. Here you can see the result, but the idea is that the RCM is also quite expensive. So with statistical downscaling, we aim to generate something like this, but in a more, without having to require that many computational resources as a RCM. And actually here you can see the process that we typically follow when working under the perfect prognosis statistical downscaling. Remember, as I mentioned before, that we have statistical downscaling, which is the approach that we use for generating high resolution projections from a GCM by using a statistical model. But within statistical downscaling, there are several approaches, and one of them is perfect prognosis, which is the one I detailed here. The idea in the perfect prognosis approach is that I take as predictor, as input, a set of large-scale atmospheric variables representing the state of the atmosphere, and I train a statistical model, for instance a deep learning model, to given this information for a specific day, for a specific time, to predict the high resolution value of certain variable, for instance, temperature or precipitation. If I'm able to have a model that learns this relationship, what I can do is, instead of passing these variables, because with imperfect prognosis, this model is learned by relying on observational datasets. So if I take this model that has learned this relationship with observational data, and instead of passing observational data, I pass the data from a GCM, what I'm going to be able to do is to generate that high resolution variable. So if I train the model with observational data in a historical period, and then I pass the same variables but from a GCM, the simulations of a GCM, the state of the atmosphere simulated by a GCM in a future scenario, for instance, I'm able to recover the surface, the high resolution variable, and thus I'm able to generate something like this, to generate something similar to what the RCM is able to simulate, but without having to run the RCM, just by running a statistical downscaling model. An interesting question that we could ask is why we use as predictors the large scale atmospheric variables. Why we use as predictors the state of the atmosphere? Well, I will not go into the details in this video. You just have to trust me that this is something that we have to do. If you want to get more details about why we take these variables as predictor and what kind of assumptions we have to deal with when working with perfect prognosis statistical downscaling, you can take a look at the notebook. Here is all of this explained in more detail. Okay, so you get like the overall picture, the overall idea on why we make some decisions in the statistical downscaling. So now that, especially after you go through the notebook, now that we have some background and some idea about the statistical downscaling and what we are doing, what we are going to do is to start working with the code. We are going to load the data from the benchmark that we talk about. We are going to prepare the data to train the deep learning models. We are going to define a simple deep learning model, DPSD. I will talk about it later in a bit more detail. Then we will train in a historical period, because remember that we train the model in observational data, so we have to train the model in a historical period. And then we are going to evaluate. And actually, in statistical downscaling, evaluation is quite important. That's why I would like you to focus on the evaluation, because when we come from machine learning, we are used to, I would say, we don't pay that much attention to evaluation, but in statistical downscaling is key, especially if we want to use these models in an operational setting. I will talk about it later. And then, well, we will use the model in an operational setting to generate simulations at high spatial resolution from a GCM in a future scenario. So here I will not go into the details of the code. I think it is a better idea if you go through the code. The code is well explained in the notebook, so you can look at the details to get an idea of what we are doing and so on and so forth. So I will give you in this video an overall picture of what we are really doing. So first we load the predictors, which in this case is a set of large-scale variables representing the state of the atmosphere, and we are going to load the predictant, which is the surface variable at high resolution that we want to downscale. In our case, we are going to focus on precipitation. Again, the data is in the NetCDF format, which is the standard for climate applications, but by using XRI, we will be able to to work with Python in a straightforward way from this netcdf data. So that's what I do here, and actually here you can see the dimensions of the predictors input and the predictant or target. For the predictors we have actually for both, for the predictors and predictant, of course, because they are aligned in time. The temporal resolution is daily. We have daily data, and we have, well, this spatial resolution for the predictors and this spatial resolution for the predictant. Of course, the spatial resolution of the predictant is larger because it has a higher spatial resolution. That's what we are trying to do with this deep learning model. Go from the coarse resolution to the high spatial resolution. And here, what I do is I just print one sample of the one day, the set of predictors for one day, and the surface variable, the variable that I want to downscale for that specific day, so we can get an idea of what the data the deep learning model is going to use to fit its parameters, its weights, right? So here you can see for this specific day, the predictors. These predictors covers an area over New Zealand. Remember that we are focusing on New Zealand. We want to downscale precipitation on New Zealand. We have, well, zonal wind, meridional wind, we have specific humidity, temperature, and we have geopotential height. So again, what we can see here is the low spatial resolution. You can see how we don't have that many values for such a large area. The deep learning model, what it has to learn to do is with these predictors, which represent the state of the atmosphere, to downscale the high resolution precipitation. So this surface variable, which is precipitation. So the idea is to use these predictors, which have a coarse resolution, to downscale this high resolution variable, which in this case is precipitation over New Zealand. So before using this data for training the model, and again, I would like to emphasize that we are trying to learn this. The predictors that I just showed correspond to these variables, and the predictant, which is the precipitation, and New Zealand is going to correspond to this variable over here. That's the idea. Now we want to use a deep learning model to learn this empirical link. So we have to prepare the data for training. I will not go into the details because this is, well, you have the details in the notebook, of course, but this is like quite basic jargon for machine learning and deep learning. But we are going to divide the data in training and validation. We are going to train the data in the training data, of course, and then we are going to use the validation to, for instance, check whether we are overfitting or whatsoever. And then once we have the model trained, we are going to test it in a period which has not been used for training. Of course, this is the standard approach. We are going to standardize the predictors as it is usually done with machine learning and deep learning models. And also I'm gonna go from XRI to PyTorch, so I can use that data for training a PyTorch model. Again, you have the details of the code in the notebook. Here I do I split the data in training, validation, I format the data for the model, and so on and so forth. And regarding the model, the deep learning model that we are going to use to learn that empirical link, we are going to use a model denoted as DPSD. If you want to know more about this model, it's quite a simple deep learning architecture. You have some references at the end of the notebook. The DPSD is a convolutional deep learning model that is going to take all those predictors, those large scale variables, is going to apply 3 convolutional layers, and it's going to take the output of the last convolutional layer, is going to flatten it into a vector, and it will pass that vector into a final fully connected layer, and the output is the the surface variable, the high resolution variable that we are trying to downscale. And here you can see the code for that model. As you can see, it's quite a simple PyTorch model. Actually, this model is quite simple. It is true that now, in the state of the art in statistical downscaling, we are moving to more complex deep learning models. For instance, now we are working with diffusion models, transformer based models, and so on and so forth. But this model, despite being that simple, it still works quite fine, and it has been used a lot in operational settings. So it's nice for you to, well, to know this model, because it has been, I would say, an important model in the statistical downscaling literature. Once we have defined the model, again, you have more details and more anecdotes about the models in the notebook. So I really encourage you to look at the notebook in detail. Once we have defined the model, we can train the model. I will not go into the details. The training is quite simple. And for the loss function, we are using the mean square error. Yes, the most straightforward loss function for regression, I would say. It is true that this is not the ideal loss function for precipitation due to different reasons, but for this case it's simple enough so you can get an idea of what kind of models you can use, and well, to get an idea of what we do with deep learning for statistical downscaling. So in this case, I have trained the model for 50 epochs. You can change this value. I think is one parameter that you can tune in that cell I mentioned before at the beginning of the tutorial. And then, well, you can do the typical visualization of the loss function and so on and so forth. Once you train the model, you can compute predictions using a different set of predictors, right? For instance, in this case, what we are going to do is to evaluate, again, you have more details in the notebook, but overall, what we are going to do is we are going to train the model in certain historical period. Actually, we are trained, and this is something I mentioned before, I think, when talking about the data set. Yeah, we are going to train the model in this period, and then we are going to do a first evaluation on this period. And the idea here is to see to what extent the deep learning model is able to downscale in a different period to that seen in training. Because you have to think that within the perfect prognosis approach, we are going to train the deep learning model in an historical period with observational datasets. And then we may apply the model to a GCM in the future. So the model has to be able to extrapolate to the future. And that, if you know about machine learning and deep learning, extrapolation is quite challenging for these models. That's why in this case, it is key to evaluate the model to see to what extent it's able to extrapolate to this period. Of course, this period is not the same as this one. The climate can be quite different between these two, but this can give you an idea by evaluating this period of to what extent the model is able to extrapolate into the future. So if we go back to the evaluation of the model, here, what we do is we just compute the predictions for that period and compare the predictions, which is the downscale high resolution precipitation, to the true or to the expected, to the observed high resolution precipitation for that period. The idea is to compare those two and see to what extent our deep learning model is doing what it has to do, which is learn that empirical link that I showed you before in the schematic figure. The thing is that one could say, okay, let's compute the root mean square error or this kind of machine learning based metrics. The issue is that for downscaling, we need to perform a more exhaustive evaluation because we are going to apply the model into the future, for instance, or we may be interested in downscaling precipitation in a region in which we have a lot of extreme precipitation. So the model the model will be applied in operational settings to quite challenging scenarios. That's why for downscaling evaluation is quite important. As an example, in this case, we will use root mean square error to get the day-by-day error, right? The overall day-by-day error. But as an example, I just wanted to show you other kind of metrics or of diagnostics that we use to evaluate this kind of models, in this case precipitation. For instance, we can compute the bias of the deep learning model with respect to the truth. This bias is generally computed for different statistics. For instance, for the mean. The idea is to see how similar is the mean predicted by the deep learning model to the target mean. But not also the mean. For precipitation, we may be interested in assessing the extremes because extremes are less common when training a model. You don't get extremes that often, of course, but they are quite important because some regions may be affected by these extremes. So if we have a deep learning model that is not able to capture these extremes, we have a problem. That's why this bias is also going to be computed for these three indices, which try to assess how well the model does regarding extremes. For instance, how well the model does in reproducing the 98th percentile, right? So in that case, we are assessing the model regarding that extreme. So in this case, we can see how we have to assess deep learning models not just to the mean state, but also to extremes. We have to be really careful with the evaluation. Here you can see some examples on how we can define these diagnostics. Again, actually, if you would like to get a broader picture of what kind of evaluation diagnostics we use, in the benchmark, you have a set of representative diagnostics that are being used across the literature in case you want to get more details about the evaluation. Because if you plan to work in statistical downscaling, evaluation is quite important. It's quite important. And also the evaluation may change regarding the variable. We may don't want to look at the same properties if we are downscaling in precipitation versus if we are downscaling temperature, for instance. So this is something that we have to take into account. And actually here you can see an evaluation that we have done of the model on this period that I have mentioned. If we focus, for instance, in the bias of the mean, we have this value. These are millimeters per day. So one could say, well, it looks fine. The bias for the mean precipitation is not that high. Well, that may be the case, but if you go to the extremes, as you can see in these other diagnostics, for instance, if we focus in the bias of the 98th percentile instead, we can see how we get 80 millimeters. So this is more concerning, I would say. But if you go to this index, which is assessing the annual maximum of precipitation, so this is trying to see how well the deep learning model reproduces like quite extremes. You see that we have a really high error. Actually, one could say that in this case, the model is not able to properly simulate, to properly downscale extreme precipitation cases. So this is something that we will need to look into more detail. In this case, probably the cause is the loss function. The mean square error is not a good loss function if you want to have or to train a deep learning model that does well regarding extremes. But I will not go into the details of that. Actually, I think that is mentioned in the notebook. But The idea here is that for the evaluation, we need to pay special attention to diagnostics beyond those typically used in machine learning, especially if we want to use that downscaling model in an operational setting. Here you can see some other visualizations. For instance, here you can see again the same biases, the bias of the mean, the bias of the 98th percentile, and so on and so forth. But instead of a single value, we get the spatial details, so we get the bias for each point. And we can see how for the extremes, we are underestimating the extremes. So this model, this deep learning model trained with a mean square error loss function, it is not a proper choice for downscaling precipitation because it is not able to reproduce the extremes. And for some regions, actually, for instance, the region corresponding to the Southern Alps, in which extreme precipitation is important due to local processes, in that case, this model is not suitable for downscaling. Again, this is quite a simple model, and in the literature we have models that are already able to downscale these extreme precipitation cases. So there are plenty of models out there that can solve this issue. So imagine that, okay, I have evaluated my model, my deep learning model, and it's working well. So what is the next step? The next step, if we go back to the schema, I have a model trained here, I have performed the evaluation, and the model is okay. It seems to work well. It works well when downscaling from large scale variables to the high resolution variable of interest. So now, in an operational setting, what I do is I take the variable from the GCM that I want to downscale, and I just apply this model. So as a result, I get the corresponding high resolution variable, in our case, precipitation. So that is what I do next in the tutorial. If we go back here to this section, we have GCM projections, and that's what we do here. We take the model and we pass as predictor a variable from a GCM. There is something I would like to mention, and I would say that this is quite important if you want to understand and to work on statistical downscaling, and that is that when we move from the data used for training and the data that we use in an operational setting, which is the GCM, there is a difference there. Not just in time, we have to extrapolate. If I want to generate the high resolution variables in the future, I have to extrapolate in time because I have trained my model in a historical period. But there is also a distributional shift between the variables of the observational dataset and the variables from the GCM, because although the variables are the same, they are the wind components, specific humidity, and so on and so forth, they are generated from different ways. The GCM has some properties that are different to those of reality because the GCM is an approximation of reality. So we have to pay special attention to that distributional shift when working with GCMs in operational settings. Actually here, what you can see in blue is the PDF it's the distribution of a predictor from the observational dataset used for training the model, and in orange is that same variable but simulated by a GCM in the same period. We can see how there is some difference in the distributions, and this kind of differences can be a problem for deep learning models because the deep learning model has been trained in the blue data. It is used to the distribution of the blue data, and if you suddenly change that distribution from the orange curve, so from the observations to the GCM, that may be problematic for the deep learning model. And actually, this is, I would say, one of the most important challenges that we are facing when working with deep learning models for statistical downscaling. But again, you have more details of this problem and potential solutions that are being explored in the notebook in case you want to get into the details. So what we do here is just we pass as predictor the variables from the GCM and we downscale in the future because the GCM can generate simulations into the future. In that way, we are able to estimate the climate change signal of a GCM, but with a high spatial resolution. And that's what we do here. Here, for instance, we have the climate change signal of precipitation for this period, taking as basis this historical period. We have the climate change signal of a GCM. We have the climate change signal predicted by the DPSD, by our deep learning model. And we have the climate change signal of the regional climate model of an RCM. The idea here is that these two should be similar. This is the result of statistical downscaling, and this is the result of dynamical downscaling. And actually what we see is that they are quite similar. So this is ideal because this means that we are able to downscale a GCM with a statistical model which is orders of magnitude less computationally expensive than an RCM. So the final purpose of deep learning models for statistical downscaling is to achieve this, to being able to, given this coarse simulation by a GCM, to produce something that has the high resolution data required to, for instance, take decisions of the impact of climate change in these two local regions. And actually we can see here that we are getting something similar to an RCM, which is a more computationally expensive dynamical approach. Of course, the interesting part of statistical downscaling with deep learning models is that we don't, actually will not go into the details, but we don't have just one GCM, but we have multiple GCMs. So we want to downscale all those multiple GCMs. Of course, if we use RCMs, if we rely on dynamical downscaling, that is not possible because this is computationally expensive. But if we have a statistical model, a deep learning model that can downscale from all those GCMs in a small amount of time, we can get the corresponding high resolution variables from all those GCMs. And in the next section, what I do is I do the same as I have done here, but with a different GCM, just to show that we are able, of course, to, given a different GCM, generate the proper high resolution precipitation simulation. So that's the idea of statistical downscaling. Again, this video is an overview. It is not expected to be as complete as the notebook, but I would say that it serves as a good introduction to the notebook. I have left some exercises. For instance, the code is modular, especially the training and the deep learning model is quite modular because I want you, if you are interested, I would like you to test other architectures, to play with the data, because I think that's the proper way of getting familiar with something, to play with it. So you have an example of a different architecture. Actually, if you take this PyTorch class and you put it where we have the DPSD class, it should work and you should be able to generate projections with a different deep learning architecture. But of course, if you are familiar with PyTorch, it's easy to play with this function and to try different models. You have some references at the end of the notebook in case you want to go deeper into deep learning for statistical downscaling. And you have a note about other downscaling paradigms that I think is important, because when you start working on statistical downscaling, sometimes you find something denoted as super resolution, which on the surface is quite similar to perfect prognosis statistical downscaling, but at the same time is a bit different. So just a note for you to know. And this is my introduction. I hope you enjoy the tutorial, and if you have any question, any curiosity, or if you would like to keep exploring the benchmark, the Cordex ML benchmark, I'm here. Thank you very much.